Hey folks, welcome to another set of Chemistry 2 video notes. Today we're going to cover Chapter 3, The Evolution of Atomic Theory. In this chapter we'll learn about Dalton's atomic theory, the first developed model for the structure of an atom, how the nucleus was discovered, the general structure of the atom, how the periodic table was first arranged by properties, what the periodic table looks like now, what ionization energy is, and how mass spectrometers help us see different isotopes. Let's get started. Remember when we talked about the first idea of the atom that occurred back in 400 BC? If not, here's a short summary. There were two philosophers, Democritus and Aristotle. Democritus philosophized that you could only cut a piece of matter in half so many times before you got down to a particle that is no longer divisible. He called these particles atoms. Aristotle, based on observations he could actually make, believed that matter is continuous and could be divided up an infinite number of times. Since Aristotle's theory was based on observations that the people could actually make, Democritus couldn't cut matter down to a single atom, Aristotle's theory was the one that people supported. It wasn't until 2,000 years later that a guy by the name of John Dalton finally came up with a formal theory of the atom. To understand Dalton's theory, you have to understand what was going on during the time. During the 1700s, there were two very important scientific laws that came about: the law of conservation of matter and the law of constant composition, also known as the law of definite proportions. The law of conservation of matter states that matter cannot be created nor destroyed when a chemical reaction takes place. This was hard to prove during the 1700s because many reactions that were performed created products that included gases. These gases would escape and it would look like you lost some mass. Antoine Lavoisier and his wife Marie are credited with being the first to definitively prove the law of conservation of matter by performing reactions in closed vessels. This allowed all of the gases to be trapped within the vessel, showing that the whole system maintains a constant mass. The law of constant composition, more commonly known as the law of definite proportion, states that multiple samples of the same substance will always contain the same percent by mass of the elements that make up that substance. What's percent by mass, you say? Great question. The percent by mass is simply a ratio of the mass of whichever element you're talking about to the mass of the whole substance. We find it by taking the mass of the element divided by the mass of the whole substance, then multiplying by 100%. So for example, if we took water, H2O, and separated it into its separate elements, hydrogen gas and oxygen gas, we might get something like 44.4 grams of oxygen and 5.6 grams of hydrogen. To find the hydrogen's percent mass, we take its 5.6 grams divided by the total mass of 50 grams, then multiply it by 100% to get something about 11% by mass. You could do the same for oxygen as well. The important thing here is that even if we started with 5 grams of water or even 150,000 grams of water, our percent mass would be exactly the same. This is what the law of constant composition says. A compound will always be made up of the same ratio of each element. So, based on those two scientific laws, Dalton came up with 5 statements or postulates about the atom. He said that all matter is made up of small, indivisible, indestructible particles called atoms. Atoms can neither be created nor destroyed. They persist unchanged for all eternity. Atoms of a particular element are all alike in size, mass, and properties. Atoms of different elements are different from each other in size, mass, and properties. And a chemical reaction involves the union or separation of individual atoms. Dalton and others at the time envisioned a ball and hook model of the atom, where each atom was represented by a ball with a specific number of hooks attached to it. These hooks are what determined how that atom would bond to other atoms. For example, a hydrogen atom only has 1 hook, but an oxygen atom has 2. So it would take 2 hydrogen atoms to hook up with 1 oxygen atom to make H2O. Dalton's theory was not accepted at the time, nor would it be fully accepted for the next 100 years or so. However, at that time it was the only theory that could explain why the law of conservation of matter and the law of definite proportions were consistently observed. 200 years after Dalton came up with his theory, we've proven that each of his statements are at least partially false. However, it was still a superb theory for the time that he came up with it. So Dalton came up with his theory, and within 100 years, most scientists had come around to his way of thinking. The development of the atomic theory really took off in 1897 with J.J. Thomson's discovery of the electron. Thomson's experiments and observations led him to believe that all atoms contain electrons, and all electrons are exactly the same. He also found that electrons are extremely small and lightweight, about 1/1836th the mass of a hydrogen atom, which is the smallest and lightest element. Lastly, he discovered that they had a negative charge, which we assign a value of -1. About 10 years later, he and another scientist discovered a much heavier particle that we call the proton. It's roughly the size of a hydrogen atom and has a positive charge, which we assign a +1. A couple of years later, Ernest Rutherford discovered the nucleus, which we'll talk about here soon. Then 23 years after that, James Chadwick discovered another particle that's about the same mass as a proton but exhibited no charge. Since it was neutral, he called it a neutron. Before we move on to Rutherford, let's talk about Thomson's atomic model. Thomson discovered the electron, and he knew that every atom had electrons. He also knew that atoms behave neutrally. They don't have a net charge. That means there must have been something with a positive charge to balance out those negative charges from the electrons. His best model of this was the Plum pudding model, which is an irrelevant name now, but you can think of it like cookie dough. The negative electrons would be like the chocolate chip chunks in the cookie dough, and then the rest of the dough would represent a cloud of positive electricity, as J.J. called it. This model became widely accepted, and chemists everywhere were using this to understand the behavior of atoms. Ernest B. Rutherford, who I assume was a super fan of Thomson, set out to prove that Thomson's theory was correct. He did this by setting up an experiment in which he shot alpha particles at a sheet of gold foil. These alpha particles were small chunks of positive matter traveling at about 9,300 miles per second towards a thin sheet of gold that was only about 2,000 atoms thick. Rutherford hypothesized that the path of the alpha particles would not be affected by the electrons or the positive cloud around the atoms. Electrons are about 7,000 times lighter than an alpha particle, so that would be like a mosquito getting hit with a freight train. The freight train has no idea the mosquito was even there. Even though the alpha particles were positively charged and like charges repel each other, Rutherford hypothesized that the positive cloud was spread out so thinly that it wouldn't be able to repel the fast-moving particles. So to set this up, he put some alpha-emitting radioactive particles in a lead box, with a small hole in it pointed towards a sheet of gold foil. Surrounding this box was a screen of glass coated in zinc sulfide, which lights up when hit with alpha particles. Here's where it truly gets amazing. Remember, Rutherford was fully on board with Thomson's model of the atom, and he was trying to prove that it was correct. If Thomson's model was correct, the alpha particles would just shoot straight through with absolutely no deflection to their path. For the most part, that's exactly what happened. But about 1 in every 2,000 alpha particles got deflected, some by extremely large angles. Imagine Rutherford and his students sitting in a pitch-black room watching this green-tinted screen for flashes of light, and they see the main spot they expected to see lit up very brightly. But then, every once in a while, there's a random flash off to the side. To paraphrase Rutherford's words, it was as if you fired a 15-inch shell at a piece of tissue paper, but then the shell bounced back at you instead of going straight through the paper. As astonishing as this was, the work that followed was even more astonishing. Rutherford had to rethink the whole idea of the atom. He had to go against what he had learned and truly believed to explain the observations that he just made. It took him about a year of more observations, intense calculations, and a lot of thought before he came up with his atomic model. He decided that since most of the alpha particles went straight through, the atoms must be made up of mostly empty space. However, in order to deflect an alpha particle at that speed, each atom must have had a small, dense, positively charged part to the atom. He called this the nucleus, which we now know houses the protons and neutrons. The electrons go in all the empty space in the atom. This illustration summarizes what Rutherford thought the gold foil must have looked like at the atomic level. To put this model of the atom into perspective, the atom would be like the whole Dallas Cowboys stadium. The nucleus would be like a ping pong ball suspended in the middle of the stadium, and then in the rest of the empty space, the electrons would be like mosquitoes flying around the stadium. Rutherford's atomic model was a great explanation for what he observed, but it didn't quite fit in with the current understanding of physics. If the electrons were moving constantly, why didn't they run out of energy? What was supplying them with enough energy to keep moving and not get sucked into the nucleus by the strong attractive forces between them and the positive protons? Classical physics would expect them to spiral into the nucleus like a piece of space debris would orbit around a planet but then slowly get sucked in. From 1910 to 1930, there were a lot of difficult questions about the atom that could not be answered by classical physics. Thus came the dawn of the age of quantum mechanics. We'll learn about this in Chapter 4. Alright, now that we've nerded out about one of the most amazing discoveries in all of chemistry, let's move on to some more nitty-gritty stuff. We identify atoms using the atomic number. The atomic number is just simply the number of protons in an atom. This number is unique for every element. The mass number is the number of protons plus the number of neutrons. All atoms of an element have the same number of protons, therefore they have the same atomic number. But sometimes they can have different numbers of neutrons. Therefore, they have different mass numbers. These are called isotopes of each other. For example, carbon-12 and carbon-13 are both isotopes of carbon. They each have 6 protons, but one has 6 neutrons, while the other has 7 neutrons. Almost all elements have at least 2 isotopes. With 2 exceptions, all isotopes are named as we named the 2 carbon isotopes here, with their name and then the mass number afterwards, or their symbol with the mass number as a superscript to the left. Either way, it reads the same, carbon-12. Hydrogen-2 and hydrogen-3 are the only 2 that have special names. These are called deuterium and tritium, respectively. The atomic mass is the actual mass of the atom. Remember, the mass number is just a count of protons and neutrons, not the actual mass. Look at these isotopes here. You might notice something a little strange. These isotope masses are reported in atomic mass units, or AMUs. 1 AMU is universally defined as 1/12 the mass of a carbon-12 atom, or about 1.66054 times 10 to the negative 24 grams. This is relative to carbon-12, therefore it's called the relative atomic mass. This is why the carbon-12 atom has an atomic mass of exactly 12, while the other atoms on this chart have long decimal numbers. While we're on the subject of isotopes, the average atomic mass is a weighted average of all the isotopes of an element. To find this, you take the percent abundance, or natural abundance, of each isotope and multiply the isotope's respective mass. Then add all of those products together. For example, carbon-12 makes up 98.89% of all carbon atoms, and carbon-13 makes up 1.11% of all carbon atoms. Multiply each of those by carbon-12's and carbon-13's atomic masses respectively, then add those 2 products up. This gets you 12.01, the average atomic mass and the mass that's reported on the periodic table. Like I said before, the 1700s and 1800s were a busy time for chemists. Many of them spent a lot of time decomposing compounds into their separate elements, isolating those elements and recording their properties. By 1860, we had solid data on about 70 of the 118 elements. Dmitri Mendeleev took the elements that were known during his time, wrote them on cards, and tried to organize them in some way that made sense. He did this because there were getting to be too many elements to not have them on an organized table. He eventually organized them by increasing atomic mass and landed on a major breakthrough. When he did this, he realized that the properties of the elements repeated in a regular way. He called this the law of octaves because he noticed that every 8 elements the properties repeated. This is also called periodic behavior, chemical periodicity, and later called the law of Mendeleev. Take sodium, for example. Sodium is a shiny, soft metal that reacts violently with water to create a base and hydrogen gas. 8 elements before that and 8 elements after that were lithium and potassium, respectively. These both have very similar chemical and physical properties to sodium. You can also see the different oxide compounds these elements make up. All of the ones in Group 1 here make compounds with 1 oxygen and 2 Group 1 elements. Group 2 reacts in a 1-to-1 ratio, etc., etc. This is another example of the periodicity Mendeleev observed. Mendeleev's table was by no means perfect. He had a lot of missing elements, and the periodicity he observed couldn't be explained using Rutherford's model. Yet another reason why we needed a new model for the atom. One amazing thing about Mendeleev's table, however, was that he was able to predict with pretty good accuracy the properties of elements that had yet to be discovered. For example, germanium, the missing element between silicon and tin, which he called eka-silicon, was found to have properties very similar to what Mendeleev had predicted, especially the atomic mass, formula and density of the oxide compound it would form, and formula of the chloride compound it would form. Our current periodic table is a bit more complete. There's a lot of info on it which you should be able to decipher from the keys on the periodic table. For now, you need to know the following. Groups are the vertical columns. They're numbered from 1 through 18 now, but have traditionally been numbered with Roman numerals. The main group elements, the purple ones, being the A group, and the transition metals, the yellow ones, being the B group. Elements in the same group or family have very similar properties. You need to know where the alkali metals, alkaline earth metals, chalogens, halogens, and noble gases are located. The horizontal rows are called periods and are numbered 1 through 7. The lanthanides and actinides there in green are parts of periods 6 and 7. The repeating patterns of properties of elements repeat every 8 elements for the first 3 rows, every 18 elements for the next 2 rows, and every 32 elements for rows 6 and 7. You can also see what state of matter each element is in at standard temperature and pressure by looking at the color of the text in each box. Lastly, 75% of the periodic table is made up of metals, which are found to the left of the red zigzag line, not including hydrogen. Nonmetals are found to the right of the zigzag line, plus hydrogen, and metalloids are all the elements touching the zigzag line except for aluminum and polonium. Metals are shiny, conductive, malleable, and tend to lose electrons. Nonmetals are usually dull, brittle, and non-conductive and tend to gain electrons. Metalloids, sometimes called semimetals, can have both metallic and non-metallic properties. For example, silicon is neither a good or bad conductor, but a semiconductor. When a particle of an element has exactly the same number of protons as it does electrons, it has no overall charge, and we call that an atom. When you add or remove an electron, the protons no longer equal the electrons, so you'll have an overall charge now, and we call that an ion. If you add an electron, you add a negative, making your ion negative. This is called an anion. If you remove an electron, you've got one more proton than you do electrons, so your overall charge is positive. This is called a cation. When you write the charge, write the value of the charge first and then the positive or negative sign afterwards. We kind of mentioned this before, but the forces that hold electrons around the nucleus, that attractive force between oppositely charged particles, is called the Coulombic force of attraction. In order to remove an electron, you have to add enough energy to overcome the Coulombic force of attraction. The minimum amount of energy you need to pull an electron away from an atom is known as the first ionization energy. The first ionization energy increases as you go from left to right on the periodic table and decreases as you go from top to bottom. We'll learn more about why that is later. For now, you just need to know that the more metallic the atom is, the less strongly it holds onto its electrons, so the lower the ionization energy. The less metallic an atom is, or the more non-metallic an atom is, the stronger it holds onto its electrons, so the higher the ionization energy. In fact, the ionization energy is so high, it's difficult to provide enough energy to nonmetals to remove electrons. So they actually prefer to gain electrons instead of lose them. You may have noticed light passing through a window at a certain angle and producing a rainbow. This is a wonderful and beautiful effect, but chemists started to find that not all light produces a rainbow. If you add large amounts of energy to gaseous elements, you can cause them to emit light. This is how neon lights work. The light that those elements give off do not create a rainbow if passed through a prism. They create distinct lines of light of different colors, which we call atomic emission spectrums. They're distinct for each element. When scientists discovered this, it revolutionized the world of physics and chemistry. We were finally able to redefine our model of the atom to something that we still use today. And physicists had to develop a whole new branch of physics to explain this phenomenon. Again, we'll learn about this in the next chapter, but for now, just appreciate all of the work that got us this far in the history of the atom. Lastly, let's briefly talk about mass spectroscopy. Mass spectroscopy allows us to separate atoms of different masses. We could separate the different isotopes in a sample of an element. We do this by running a vaporized version of the element through a mass spectrometer. The particles in the sample get ionized, they become charged, they get accelerated, and then deflected by an electromagnet. Finally, they land on a detector at the end of the spectrometer. The angle in which the particles get deflected by the electromagnet is largely dependent on the mass of the particles. This is how the heavier particles get separated from the lighter particles. Eventually, you get a graph that looks like this, where the relative mass to charge ratio is indicated on the x-axis, and the relative abundance of each isotope is indicated on the y-axis. You can use a graph like this to estimate the relative abundance and the atomic mass of each isotope. You can then use those estimated numbers to calculate the average atomic mass of the element. Well, that's all for today, folks. I know that was a lot to cover in such a short time, but as long as you pay close attention to this video and take the time to read this chapter in your book, you should have no problem as we practice and eventually test over this material. As always, let me know if you have any questions.